this. Perfect.
Kamil, you can start your presentation just to see if you can share your screen.
Huh? Bang, bang, bang. So here it is. Share screen. So
okay, everything is okay.
Right.
Okay.
At last.
We can check if you can, if I see your video. Okay, I see your screen in, now. Oh, okay.
Everything is okay. Okay. We can check if you can.
Okay, everything is okay. So we still have 8 minutes to the beginning.
That's good. It's very smooth today.
Yes.
What's the delay on YouTube? It's 30 seconds, it looks like.
Yes. We have 30 participants already.
Wow. It's nice. So, okay, I switched to camera to say to the students at least hi, and then I will start sharing my screen. It seems that everything works so smoothly. I'm so stoked. I can see myself.
It looks like today it's really nice day.
Yeah, it's a beautiful day. The humidity outside is here very high. It's like in sauna. But, good. For some reason, I'm not able to start video.
Why?
Don't know.
And now try.
Video, yeah. Well,
So,
life is never so smooth. Doesn't matter.
do you see a question to start your video? Or?
Well, I saw it, but for some reason it disappeared. Share screen.
Okay, I will try once more.
Start my video. Who knows? At least I'm able to share my screen.
Yes, I see your screen.
That's great.
Okay, and it is on YouTube. And
So please give me a signal that I can go.
yes, I think we can start.
Wow, great.
We already have 69 participants.
Great. So I will start immediately. Where is my Slido? So welcome all back to the course on Bayesian modeling. Yesterday we talked about some basics of the Bayesian modeling, what the prior and what the posterior distribution is, and today we will immerse into the topic of Markov chain Monte Carlo. This is very important for us because if we use Stan package or PyMC3 package or BAX or WinBAX package, these all employ the Markov chain Monte Carlo sampling from the posterior distribution. Recall, in Bayesian modeling, we have a prior distribution which summarizes all available knowledge about the inferred quantities before we incorporate new data, new observations, new measurements. Then we obtain the posterior distribution. While we usually know what the prior distribution looks like, whether it's a Gaussian centered at zero and with a huge variance, we sometimes do not know what's the form of the posterior distribution. We know its functional form, but we don't know what its properties are, what the shape is, what the mean value is, what the variance is, etc. So the goal is to sample from the posterior to obtain some histograms and to have some idea how it looks like. Introduction to Markov chain Monte Carlo. I will talk about the basic Markov chain Monte Carlo. However, Stan uses some special modified version, which is called the Hamiltonian Monte Carlo. It's slightly more complicated than the basic MCMC, so I think that starting with MCMC is a good point for you if you decide to study the basics of Hamiltonian Monte Carlo in the future. All Markov chain Monte Carlo methods are based on Markov chains. The Markov chain, you can read it here. The Markov chain is a sequence of correlated random variables, x1, x2, up to xt, such that each of the random variables depends only on the previous one. You may imagine this as a mood. Your current mood is influenced by the previous mood, but not by some historic moods. Or if you drive a car and you shift gears, the current gear is usually influenced only by the previous gear. If you change gears and you have fourth gear, then you change either to 5 or 3 mostly. So this is the one-step dependence. The transition probability describes the Markov kernel. Again, we may look at this as with the gear problem. The probability that you shift from 4 to 5 is some number, and this number is probably much higher than the probability then that you shift from 4 to 1 or from 4 to reverse. So this is the Markov kernel. It describes the probabilities of going from one state to another state. It's a probability, so it must be representable by some probability distribution. And if probability distribution, then there is some probability density function. In this case, I describe it by Q. A bunch of emails. I describe it by Q. So this is the probability of moving from the current state xt to the future state xt plus 1, of shifting from the fourth gear to the fifth gear, of shifting from the fifth gear to 1, etc. I found a nice video about the phenomenon. It's on YouTube. I will switch the music off. Here is some guy, and there are 2 bottles of water, and he will put there some color, and we can see what happens. The particles of the color will change their position, their state. The position is the state. So you can see that the color is just transported in the glass of water. This one is cold water. So there is some transport, some transition probability of moving from one position to another position. This bottle, this glass contains hot water. And the probabilities of moving from one position to another position is completely different. It's called the Brownian motion, by the way. The Brownian motion is a Markov chain. So I can close it and go back. As an example, we may assume the Gaussian random walk, which means that I'm at some point xt and add some Gaussian, some realization from the Gaussian distribution, say 0, 1, but it may be completely different. And by addition of this random sample, I move to another point. This is exactly what happens in the glass. The particle is at some point and it's moved by some say noise to another position, and hot water or cold water, it's only about the variance. It's important the random walk is not a systematic walk, so there is just 0 mean. So the kernel here for moving from xt to xt plus 1 is the Gaussian distribution centered at xt and some noise variance, some variance. In the cold water, it would be a small number because the particles are, say, lazy and they are moving. In the hot water, where there is much more energy of molecules in water, the variance will be much higher. Here I have a code that generates 2 random walks. It generates 50 samples, starts from zero, and in one case it adds the zero-centered random number. And in the latter case, it just sets the Gaussian at the point, in the last point, and samples a new point, which is perfectly the same. But the realizations are, of course, different because it's a random sampling. So if I run it several times, we will see many different realizations. By the way, this is the Gaussian random walk, and it's the Brownian motion. In fact, it's a model for Brownian motion. An important property, a very crucial property of Markov chains is that sometimes there exists the stationary distribution. Stationary distribution is a long-run distribution. It's a limit distribution. Again, if you imagine your gearbox, you have a new car and calculate the probabilities that you shift from 1 to 2, from 1 to 3, from 1 to 4, from 1 to 5. In the beginning, the probabilities will change because you don't have any initial, or yeah, you may say that in the beginning you will say that all these probabilities are uniform, but it's a nonsense. I will probably not shift from 1 to 5 directly or from 1 to 6. So if you write down these changes and calculate the probabilities, it will evolve to some point. At some point, the probabilities of shifting from 1 to 2, from 1 to 3 will be nearly constant, assuming that you travel still on the same type of roads and the same towns and cities, but the probability will generally converge to some number. The probability that you switch from 1 to 5 will converge to 0. The probability that you switch from 5 to 1 will again converge to 0. But the probability that you switch from 1 to 2 will be quite high. And at some point, the probabilities will remain unchanged. So after reaching the stationary distribution, say f, then for every state xt from this distribution, the next state will be from this distribution too, which means the probability of the states will be the same. The chain follow the stationary distribution forever. So, and the Markov chain Monte Carlo method for sampling from the posterior distribution is generally about exploiting this effect. The goal is to construct a Markov chain whose stationary distribution is the distribution of interest, the posterior distribution mostly. So that we run a chain and it generates samples from the posterior distribution. So it's very smart. By the way, here you can see the sequential nature, why it's complicated to parallelize sampling from the posterior, why the sampling or the compilation of the code takes so much time, because it's sequential, one by one. So the Markov chain Monte Carlo algorithm, it has 3 crucial steps or cornerstones or facets. There is a target distribution, for instance, the posterior distribution, with a density f. And we want to approximate this distribution by samples because it's some complicated distribution. And we want to approximate it by samples to be able to plot histogram and to say, wow, it's a nice bimodal distribution. For this purpose, we construct a Markov chain K, which describes the transition from xt to xt plus 1, and its stationary distribution should be our distribution of interest, our target, our posterior. Because if we run if we run a Markov chain with this kernel, it generates samples from F, and we simulate the Markov chain. After we simulate it, we obtain the trace plot we saw yesterday, and by plotting a histogram of this trace plot or this trace, we will have an approximation of the, say, posterior distribution, posterior density. Mostly as the Markov kernel, we exploit some probability distribution or density that has some nice properties. The most important property, or the most important, it's questionable what's most important, but an important property of this density is that it's easy and computationally cheap to sample from it. You saw that it takes time. So the more computationally demanding distribution, the more time you will need for sampling. And generating, say, 100,000 samples takes time. Quite surprisingly, we are not very limited in this choice. There are many useful distributions that can do this, and the Gaussian distribution is very popular. Well, the most basic Markov chain Monte Carlo algorithm is the Metropolis algorithm. It has a very interesting history regarding the name, because there were some other people more involved in proposing the algorithm, but well, now it's the Metropolis algorithm. You can read more about it on Wikipedia. The algorithm for generating samples from the target density F. I just hope that I have a correct link to Slido. Hopefully, yes. So the algorithm looks like this. First, we initialize our how to say, our problem or our setting. We select a suitable initial point x0. Hopefully in a region where the target density is concentrated, but maybe we don't hit this target very well and have to converge, which means we have to discard some proportion of some part of samples. So we have an initial point x0 and select some proposed density, say the Gaussian one. And then sequentially, we generate a new proposed point from the proposed density. We calculate the acceptance probability for this x bar. The probability of transition to this new point. The probability of transition is alpha. It's minimum of 1 and this fraction. Why there is minimum? It's obvious, because the probability needs to be at most 1. Then we generate some random number from the uniform distribution between 0 and 1, which serves just for deciding whether this alpha is greater or less than this u. If it's greater than or equal to u, we accept the new sample. Otherwise, we copy the previous sample. I stress that we copy it. So it may happen that a wrong setting may produce a sequence of the same values. The chain can get stuck. some point and generate this point for some time. It's somewhat hard to think about why this alpha. What does it represent? I will try to shed some light on it in this figure. So here I have, we'll start with this. Here I have a target distribution, say the posterior distribution. Let's use the standard Laplace for it. It's the Laplace distribution. And I have some proposal. I first chose the initial point to be at 2. Here I center my Gaussian proposal. The Gaussian proposal has a constant scale. It's important. Constant variance or standard deviation. So I center it here and sample a new point from this blue Gaussian. Of course, most samples will be around the mean, and to the tails, the samples will be less frequent. So say that I sampled value 1. This is the green line. The fraction is new probability density of the new sample, proposed sample, divided by the previous. So the target probability density. So I do calculate the fraction of this black line, think of this black line, and this green line. So I may say that the probability of moving from this point to this point is quite high. Sorry, the fraction is vice versa, green divided by black, which is quite high, and it's very likely that I will accept in this point because I'm moving towards the region where the probability density is high. On the other hand, if it were vice versa, like this, there would be a fraction of the green one and the black one, which is quite small number. The probability of moving here or accepting 2 is lower, but it's positive. It's still positive. So I may accept it, but the probability of accepting this point is smaller. What's important here is that the variance or the scale of the proposal matters. If the proposal, they're the original numbers, so it's quite reasonable setting this one. If I change the proposal to be more flat, say like this, the blue is now the proposal, it's very, very flat. Then there is a high probability that it will produce produce two samples in this region, which is nice, so that the probability of moving from 2 to say -1 is very high. On the other hand, it can produce many samples smaller than 4, bigger than 4. But there, the probability density, the target probability density is very low, so it may get stuck. On the other hand, if I change the proposal scale to 0.5, maybe even less, 0.1. If I change to 0.1, most samples from the proposal will be generated here in this tiny interval. And the probability of moving from this point to this point is very high. The probability of generating samples here is very low. So the chain will converge very slowly because it will need many samples to move the proposal towards the maximum of, or the place where the target is concentrated. So this is how the fraction here may be represented. The sampling from the uniform is quite easy to understand because here, say we have a probability 0.75, and now the question is, how can I choose with 0.75? How to decide whether accept or not accept the new point? The probability is 0.75. So I generate a number and check whether it's from 0 to 1, and I check if it's less or equal to 0.75 or not. It's just only for decision, this 0.3 and 4. What generates the samples is are these 2 points, 1 and these 2 steps, 1 and 2. Good. Still no questions? No questions yet. As an example, let's try to generate samples from the Laplace distribution. So it's this red one. I want to generate samples. As a proposal, I will use the Gaussian distribution centered at xt, so at this last point, and with a constant variance. Because in software, we usually don't, the software usually does not represent the normal distribution or the Gaussian distribution with variance, but with standard deviation. I don't know why, because in probability and statistics, it's usual to use variance, but here it's standard deviation in SciPy. So I will use normal distribution with standard deviation of 1, which means it's a standard normal distribution. I will generate 10,000 samples and start from 0. The steps are, I propose a new point, step 1, I propose a new point, calculate the fraction alpha, which means I select from 1 and the smaller of 1 and the fraction, generate a uniformly distributed number or number from the uniform distribution, and decide whether I accept or whether I copy, that's the important thing, copy the last point. Bang, if I run it, here is a trace plot of the Markov chain. You can look at it as a generator of a histogram. The values here on the y-axis, 2.5, 5, in this case probably some 6, in this case probably some minus 7.8, etc. are those values on the histogram. So the histogram here is a histogram of y values of the Markov chain. The Markov chain runs, this is the time or steps, 2,000 steps, 4, 6, 8, and 10,000 steps. And these are simulated values from the target using the standard normal distribution. If you look at this graph, the orange one is the target, the Laplace distribution. There's something strange here, but it should be perfectly smooth. The blue stars here, the bars represent the samples, the histogram of the samples, and the red line is the mean calculated from the samples. The target, the Laplace distribution, has a mean 0. So I think it's quite solid. If we change the proposal scale, say to 0.1, what will happen? Because the proposal is very concentrated, it tends to change, to have trajectories here, because it moves on the target. It moves. So with 10,000 samples, you can see that it's not very perfect. This is clearly bad setting. Whenever you see such a trace plot, it's very likely that your proposal is too concentrated, too narrow. It was the case where there was this setting. So the proposal generates samples which are accepted very often, but to move the proposal here means that you need to generate many samples, which generates this trajectory. If you have a large proposal, it's too much. So the standard deviation 5, oh, it's the solid. So let's put there something extreme. If we have a large proposal, 50, which means that the Gaussian distribution, I will put here just 5. The proposal generates very likely samples here, there, and here, and there. Most of them will be rejected. Most of them will be rejected. Then we have, then we can observe these constant periods, where the last position of the proposal is just copied because the new sample is rejected. The new sample is far from the current, which may indicate that you sample on tails. So this is how it works. Fortunately, Markov chain Monte Carlo methods are not overly sensitive to settings, and you can always investigate the trace plots. And there are some patterns that say, well, this is wrong or this is wrong. Well, we have 2 questions here on Slido. The kernel is like a vector of distributions. No, the kernel is just one distribution. It's just one distribution, in our case with a constant variance and with a mean value, in the case of the Gaussian distribution, with a mean centered at the last point. So it moves on support of the target distribution. The second question, how do you choose the target distribution? Shouldn't that be the goal? The target distribution is a distribution you want to sample from. So in the Bayesian statistics, the target distribution is usually the posterior distribution, because we are interested in posterior distribution, because it represents our knowledge of something that we want to estimate. For instance, if we want to estimate the intelligence quotient of a population, then the target distribution is normal and centered somewhere at the mean. And if you want to estimate this mean, we use prior distribution, we feed it by data, we obtain posterior distribution for the mean, and then we say, well, the mean is 100, and or the expected mean is 100, and the variance indicates that with some probability it may be between, say, 98 to 103. So the target distribution is a target. This is why we do this. Roman, just to make sure, the goal of MCMC is to make approximation of some complex to sample distribution into something that's easy to sample from with the same characteristic as target. And because of the iterative nature of the Markov chain, it's impossible to parallel compute. I will start at the end. The iterative nature of the Markov chain really prevents the parallelization, because the Markov chain, if I go here, or maybe even here, the Markov chain says you have one value, try to move to another value. You have another value, try to move to yet another value, and so on, still based on the previous value. So the Markov chain really depends on the previous state. It's like if you go drunk from a pub, you generate a random walk, and you can't parallelize yourself. You have to random walk to your home just sequentially, step by step. Sometimes you tend to the right, sometimes you tend to the left, maybe even back. It's a random walk. The random walks are sometimes called the drunkard's walk. This is why it can be parallelized. Or there are some way how to parallelize the problem, but the Markov chain itself can be parallelized. And the first part of the question, just to make sure, the goal of MCMC is to make approximation of some complex to sample distribution into something that's easy to sample from. If you have the posterior distribution, yesterday we estimated, for instance, there was time to arrival, time to event. Yesterday we estimated lambda, the rate of the exponential distribution that describes time to event. If we know the parameter lambda, then we can say, for instance, when do we expect the future event, in which time, or at which time. So we want to estimate lambda. Because we have some finite size of measurements or observations, we can't, or we can, okay, say that our lambda is some estimated value, say 50. But we are not sure about this 50. And so we want to express the uncertainty by some distribution. This distribution says, well, I have old figures there. This distribution may say it's 50, say plus minus 3. Let it be a Gaussian distribution, for example. If it were a Gaussian distribution, then it would be very easy to say what the mean is, what the mode is, what the variance is, what the range is, where the interquartile range is, what are the deciles or quartiles. So it would be very easy. But mostly the posterior distribution, unless we use conjugate priors, the posterior distributions are complicated, are non-standard. You can't look into Wikipedia what the mean of something non-standard is. You can calculate the mean value by integration, but if you have some gamma functions and beta functions in your integrals, you will be a very unhappy person. So instead of trying to do this mathematical hell and analytic integration and so on, a way is to sample from the posterior distribution as you sample from the posterior distribution, because you know that if you plot, say, histogram of the samples, it tends to the true probability density that we don't know. We know it's a functional form, but we don't know, we can't say plot it, or maybe we can plot it, but we can't say what the mean value is, because calculating the mean value means integrating the posterior density, and the integration may be very difficult. But if we sample from it, we can calculate the sample average. And we know from statistics that the sample average tends to the true mean. This is why we calculate sample averages, because they tend to the true mean. The sample average expresses some important property of the data. So this is why we do it. We have some difficult, nasty, strange posterior distributions, which are non-standard. Even if you multiply, say, binomial model for the coin by say, Cauchy prior distribution, the result would not be integrable at all. You want to do these things. So that's why we do it. How proposal and target relate to prior and posterior. Proposal is completely something which is completely unrelated to Bayesian, to the Bayes theorem. Proposal is just a tool for sampling from the target, and the target is the posterior distribution. So once I do the Bayesian update by running the Bayes theorem, I obtain the posterior and use some convenient tool for sampling from the posterior in order to look at the histogram. Wow, the posterior distribution looks like this histogram. And to say, wow, the sample mean, sample average of these samples, which I use to plot the histogram, tends to the true mean. So I can say that the true mean is, say, 5. So this is how the proposal and the target relate to the posterior. The prior, okay, you may sample from the prior, but it doesn't make sense. So that was this question. Should we always eyeball the behavior of a proposal, or there exists some useful metric for this? Fortunately for you, the proposal distribution is something which the software usually cares about by itself. So you usually don't need to specify proposal. Wrong definition of stationary distribution. Transition probabilities don't converge. They, they are fixed once and forever. It's probabilities of finding the system in a particular state that converge to the stationary distribution. Generally, I don't have perfect mathematic definitions here. There are some important properties of chains to reuse stationary distributions. Well, I skip the mathematical details because we can't cover these details in 90 minutes. By the way, I have 2 lectures at the university about stationary distributions. There is much to talk about. So the target distribution is the posterior. So the target distribution is the posterior distribution. Yeah, the target distribution is usually in Bayesian statistics. The target distribution is mostly the posterior distributions. Sometimes the posterior predictive distribution. And the posterior distribution is computed from Bayesian inference. Yes, exactly. So MCMC don't do Bayesian inference, right? It is always to sample the result from Bayesian inference. Well, MCMC is a tool for obtaining samples from the posterior distributions. Yes. MCMC itself do not represent the Bayesian inference. Although we may use MCMC in the Bayesian, in the Bayes theorem quite wisely, but MCMC is a tool. It's a tool for sampling. We have another tool for sampling. We have rejection sampling, we have importance sampling, and we have MCMC. It's a tool. Well, thank you for the questions. So let's move to the first issue. The first issue is autocorrelation. You know perhaps what IID means. It's even a buzzword. IID. Everything is IID, although most things are not IID. IID means that the samples are independent, or variables are independent and identically distributed. If I generate samples using SciPy from, say, Gaussian distribution, I would say that they are independent and identically distributed. They have the same distribution because I opted for some distribution, and they are independently sampled. Is IID the case of MCMC samples? Well, how do we generate samples using MCMC? We sit at some point, propose a new point, accept or reject it, then we move to that point and sample or propose another point, etc., etc., etc. So there is some path. The samples are clearly not IID. They are not independent. Maybe identically distributed, but not independent. This is sometimes a problem, and we want to suppress this correlation, the dependency among samples. If we look at the autocorrelation, which says the correlation of the of the chain with itself lagged by 1 step, 2 steps, 3 steps, etc. You can see that the correlations called autocorrelations look like this. So the current and the previous realizations have correlation about 0.9. The current and the pre-previous have correlation 0.8, etc. So this is clearly not IID. There is a strong correlation. In order to suppress this autocorrelation, we employ it looks like a toy tool, but it's very wise or smart solution called thinning. We save only every nth sample. So thinning means that I am at some point, I generate next point, then I generate next point, and I drop the sample that was in between, if it's thinning of 2. The period of thinning can be set by the user. Of course, there is some overhead. If you have thinning 2, it means that if you generate 100 samples, you end only with 50 samples, because you save only every other sample. The higher the thinning, the smaller autocorrelation, but the higher overhead. Here I have thinning of the original chain of this chain. So if I run thinning, here it comes. Now my trace plot, the original was 10,000 samples. Now I have thinning equal to 5. So I save only every 5th sample. So I have only 2,000 samples from 10,000. You can see that the autocorrelation, there are just 1, 2, 3, 4, the autocorrelation is significant only for subsequent samples, not for, say, 20 or 23. Just 4 samples are correlated, or the depth of correlation is 4 lakhs. The trace plot looks still fine. Why not? The histogram is still fine. The sample mean moved to some positive number, tiny positive number. So it's not so perfect as previously. In order to have a better sample mean, we would need more samples than 2000. So we would generate, say, here I had 10,000 samples. We would need, say, 50,000 samples. We may do a thinning of some small thing, 2, still not perfect, but here's how it works. And the autocorrelation is significant to like 9. So this is thinning. If you want to set thinning in Stan, it's very straightforward. So issue 2, width of the Markov kernel. I already showed you that if you use a very narrow Markov kernel, very narrow proposal, there will be trajectories in the trace plot. Looks like this. Here I had the target being the normal distribution, standard normal distribution, and the proposal was normal with standard deviation 0.01, 1, and 100. So how it looks? 0.01, which means a very narrow target, very narrow proposal. It travels, and the trajectory is pretty obvious. So this means that the proposal is very too concentrated. The samples from the posterior do not resemble anything like the standard normal distribution. The autocorrelation is incredibly high. There is no thinning. This is the case where the proposal has the standard deviation of 1. We can see quite reasonable trace plot for just 1,000 samples. We can see that the generated samples from the target, which is a standard normal distribution, yeah, I see something like standard normal distribution here. And the autocorrelation is significant up to 7 lakhs, not more than 30. If we choose a very, very wide proposal, which means it generates samples, or it proposes samples from the tails of the target, and the probability of acceptance in the tails is very low. So we can see these constant periods. There was 1, there was 0, 0, 0, very long time, 0, then there was one switch, and again a constant period, and again a constant period. So this is a trace plot of typically a very, very wide target. And you can see that the histogram does not represent anything like the standard normal distribution. Again, the autocorrelation is due to these constant periods very high. The problem of this is that we may want to increase the acceptance. For increasing the acceptance, we will use a more concentrated kernel proposal. By the way, kernel and proposal is nearly the same, or I use it for the same thing. So if you have a concentrated proposal, it tends to accept every new proposed sample, but it needs some time to travel through the target because it's too narrow. On the other hand, if we want to explore the exploration ability, that is to just generate samples from the whole target. For this, we would like to use a wide kernel, but the wide kernel is prone to getting stuck because it proposes very often it proposes samples that lay in the tails of the target distribution. So this is about the width of the Markov kernel. Next issue is initialization. If we start the exploration of the target, say standard normal distribution, mean 0, standard deviation 1. If we start at 0, then the situation is great because we are in the region where the probability density function is high. But what if we start the exploration, say at 100? It's very far. It's on tail of the normal distribution. Then the Markov kernel will need time to travel. Here I have an example. I have again it's the same code as I showed above. The target is the Laplace distribution. The proposal is normal distribution with scale 1. If I started from say 5, just 5,000 samples, it will look like this. Wow, it's burning, sorry. If I start from say 5, so I started and the target from the value of 5, it's here. It's okay because the Laplace distribution, there it is. So for instance, here 5 is here. The Laplace distribution here, it's very this position is very close to the region where the probability density is concentrated. It's fine. But what if I start at 100? 100. So it takes a long time to move the proposal to the region where it's sensible to sample. So here you can see that the Markov chain Monte Carlo proposes values closer and closer and closer to the Laplace distribution, where the Laplace distribution has most of its probability density. What are these samples? These samples would cause a problem. You can see that the calculated mean here is very, very biased. The true mean is 0. The orange line depicts the target, the Laplace distribution. The mean should be at 0, but it's very far from 0. So the idea is to drop some initial samples. It's called burn-in. In Stan, it's called warm-up. I will drop 500 samples. If I drop 500 samples, which means I start to save my simulated quantities just here. The the samples really really resemble the Laplace distribution. So this is the burn-in. Just drop the initial period. All these three things you can set in stun and sampling the burn-in, how many samples will be dropped. The thinning, what's the period of saving samples to suppress correlation. And what was the third thing? Burn-in. Yeah, and the Markov kernel. You usually don't set the Markov kernel. It's the standard does by itself. Monitoring of convergence is very complicated thing in Markov chain Monte Carlo, since the topic was developed. There are many papers about monitoring convergence. When do we say that the Markov chain converges? When do we say it does not converge? It's very complicated because how to say that this trace plot is really okay. In this case, we are lucky because we know what the target was. I said that this is a standard normal distribution, but we don't know this always. Sometimes we don't know, and then we could say, well, this histogram, does it resemble the posterior distribution? I don't know. I can see from this development that probably not, but I'm not sure. So there is a problem of monitoring convergence. There are many possible ways how to do it. The most basic ones are look at the trace plot. Is the trace plot something like a hairy line? If yes, well, it's good. If not, if there is some trajectory, or if there are some periods of constant evolution, then there is a problem. Look whether there is something like this. Then it certainly needs to drop these samples. Often we run 2 or even more chains. If we have more chains and we check that the chains lead to or have virtually the same histogram, or at least very similar histograms, then we may combine the samples. This is, by the way, a way how to generate more samples, how to parallelize the thing, just running more chains. Some methods exploit dividing the generated chain into some, say, periods or groups, and check whether the statistical properties of some group and some subsequent group are same or whether they differ. If they differ, then the Markov chain Monte Carlo has not converged, probably. If they are the same, it has converged and generates samples from the same stationary distribution, which means from the posterior distribution, if we are lucky. Additionally, there are some other convergence monitoring techniques, like the number of effective samples. You saw it yesterday. Another way is the Gell-Mann's statistics. Well, generally, stun will tell you that something went wrong if something went wrong. Sometimes it doesn't tell you, but you can say it from the evolution of the trace plot. So that's it. If you want to know more about monitoring convergence, there is a section 50 in the Stein manual. Quite unfortunately, it's not very dense on the topic. Oh, it's not 15. It's something, some different part of the manual. Maybe it changed. Yeah, but there is some monitoring of convergence. It's important that the software has some specific settings always, whether you use Winbugs or whether you use Stan or PyMC3, for instance, efficiency tuning. There is how to tune the efficiency so that the sampling is more efficient than without this, like reparameterizations. That's a very popular way. Or using conjugacy, you saw it yesterday. There is some part on parallelization which you may try to study. Today I will talk about the regression models, and I will show you the basic linear regression model and its estimation. But there is some reparameterization which stabilizes things quite a lot. So today we will have for example, if you wanted to perform linear regression with Stan, then this QR reparameterization is a very good way to go. So this is how it works. If you have any questions, please send them to Slido. I was surprisingly much faster than I expected. And if not, I think that we can make a pause.
Okay, so it looks like there is no question, so we have 15 minutes break, okay? Okay, thank you.
So should we start?
Yes.
Okay.
Can you share your screen?
So Nadia, I see that there is recording paused. Great.
Yes.
So I will proceed. I don't know whether you see me.
Yes, I see you.
Great. And we are online, right?
Yes.
Great. So for a moment, I will talk just in person to be seen as a real living organism and not some artificial intelligence in background. Well, intelligence. I'm not very modest. Okay, I will go through your questions just from the beginning to the end. There is a question from Anonymous. In order to apply MCMC, we need to know the target distribution. That is, to be able to compute fx. How do we compute effectively for the posterior? Well, the important thing is, if you imagine you multiply the model and the prior, and the result is a function of the unknown parameter. So effectively, you may sample from the prior and propagate it through through the formula, which means sample from the prior, multiply by the model, and you will obtain a sample from the posterior. So this is very effective. You just feed the base formula with samples and obtain posterior samples. So to say it explicitly, you don't need to calculate the functional form of the posterior. You just sample from the prior, send it to the model, obtain posterior, and after that you will have many samples from the posterior. So this is how it works. Next, Roman. Thanks for explaining. Now everything comes together. Looking forward to the regression section. Great. What are advantages of Hamiltonian over Monte Carlo Markov chains, MCMC? The basic Markov chain Monte Carlo or the Metropolis algorithm is the really most basic approach. By the way, Monte Carlo started with the construction of the nuclear bomb. You can read more about its history on Wikipedia. It was connected with Project Manhattan, and Monte Carlo was an acronym for it to make it to keep it private. So the basic Markov chain Monte Carlo, the Metropolis algorithm, is really something very basic. There is more advanced algorithm than the Metropolis algorithm. Is the Metropolis Hastings algorithm, where we don't need to use symmetric kernels. The symmetric kernel is, for instance, the normal distribution. It's symmetric around its mean. But sometimes you may want to use non-symmetric. And for this, we may employ the Metropolis-Hastings algorithm. Another modification is the Gibbs sampler. The Gibbs sampler proceeds on marginal distributions, and it converges with each step. So this means there are no stucks, which are no periods where it gets stuck. The Hamilton and Monte Carlo calculates, if I remember correctly, it calculates what calls the first derivatives. It optimizes its evolution, or the evolution of the chain, so that it converges much faster. And there are yet many other variants of MCMC algorithms. The basic one that I explained in the lecture is really the most simple solution, and it suffers some drawbacks. So the Hamilton and Monte Carlo is much better. In addition, some algorithms do not need to calculate normalizations. I think it's the case of the MCMs, of the Hamiltonian algorithm too. This is why you can use improper priors. Well, we haven't talked about improper priors. These are priors that in fact are not probability densities, because they don't need to integrate to one. So that's it. This is why we usually employ some smarter algorithms than the basic Metropolis algorithm. Next, we have here Natalia. I want to ask about issue 2 from the previous lecture. Can we use fading scale to solve this problem? I mean to start from a big scale and make it smaller and smaller during the iterations, like the exploration parameter. Yes. It's called adaptive Monte Carlo. We adapt the scale of the proposal distribution in order to increase the acceptance rate. It's a popular approach not only in MCMC but in important sampling too. I wrote a paper about some Monte Carlo method with adaptive proposal. Yes, we can use it. However, if we do this, we have really to be careful about what the sampler proposes or what the sampler produces, because sometimes may produce samples that actually do not obey the target distribution, but some modification of the target distribution. But yes, essentially, the adaptation in general was a big topic in MCMC in the last three, maybe 4 decades, especially when the computational power was not so big as today. You saw that generating 100,000 samples now is just like Bing, but in the past it took much more time. So next question from Roman, part 1. Also a little question on technicalities of Python. As far as I understood, when we generate a C++ model with Python stan model, we just compile the code without any modeling in behind. Well, honestly, I'm not very familiar with how it works in computers. I'm not a software engineer, so I know only the theory behind. But if I'm correct, the way is that the C++ code prepares the sampler, because you don't need, well, what you have defined in the model, I will share the screen. Come on. One here. You can look at this. And where is here is the model. In the model, we have defined what is the distribution of data up to the unknown parameters. We have defined what the prior is. This is perfectly sufficient for compiling a code, because you have a prior, so we know what we need to sample, what we need to use for sampling. We have a model and only send their data. All it eats in this case is just data. So we can prepare C++ code, which we feed only with data. I hope it works like this. Yeah, it definitely does. Part 2. And the real use of MCMC comes in fit sampling. My point being, it's right now just compiling model to C++ takes a lot of time and not MCMC itself. Yes, I have tried going through the source code, but it failed to understand. Yes, the thing is that this sampling is pretty fast. And why? Because we just feed the true data to our C++ code, and it then runs by itself. All you need in this case, all you need is just this in the model. This is the only external thing. The rest can be prepared in the code. This can be prepared in the code. The generated quantities are completely prepared in the code. All we need is just the data. It's similar to if you use some sklearn package or stats models. All you need is just feed some code with your observations. Everything else is performed inside the code. You just feed the data, the observations. Every clustering, every estimation, etc., is performed already within the code. So that's it. Here we just, it's similar to maximum likelihood approaches. All you need is just to put the values of the data to the likelihoods. The rest is the rest performs the software. Olga, does Bayesian modeling work numerical type of data only? What's about categorical, which are very important for clinical research? And in this context, what is about dimension of the data? Well, the Bayesian modeling, or generally the mathematical modeling, deals with numerical variables, with discrete or continuous. If you have categorical variables which describe categories, say, then you need to encode it into numbers. Essentially, it's a random variable. A random variable is a mapping from some space omega of random events to real numbers, or say real numbers. It may be more general. So if you say whether some drug was used or not used, you map it to 0 and 1. It's similar to the coin example, or the coin example head tail. Head is 1, tail is 0, or pink. With pink we had yesterday we modeled the pink, and it was either successful 1 or there was a failure, which was 0. So that's it. This is how it works. I'll stop video because my computer gets hot. So this is, there's, by the way, there is something called one-hot encoding in machine learning. And this is a way how to encode variables that are not, that do not have any ordering. Just, yeah, you need a numerical representation. Anonymous question. What is the cutting edge research in Bayesian modeling? Cutting edge. It's really hard to say. Maybe I will switch back to me. Come on. The cutting edge research. It depends. There are many different. It's like with machine learning. There are many different fields where the research is employed. Now, one of the important topics is a huge model space. If you have, yeah, this is typical. If you have a problem, you may have one model or two models or maybe three models, black box models, gray box models, physical models, etc. Imagine the problem of weather forecasts. There are many different models for forecasting. Here in the Czech Republic, we use an Aladdin model, and people often check the Norwegian Clara, I think, model just for the same place. Two models for the same place, sometimes providing two different, and sometimes very different weather forecasts. In heavy machinery and industry, there are often many ways how to model some process. In the past, I was involved in an applied research, and we had 4 models for the same thing. There were black box models, there were gray box models, which means the gray box you use some knowledge of the process, while in the black box models you use just what you have measured and to hope that there is some causality. We had physical models, and now the question is, should we choose just one model, or should we choose multiple models and try to combine them? Yeah, it seems that the combination of models in some smart way could be very good. Those of you who are familiar with model badging and model combinations, you know that this is popular in machine learning and data science. In the Bayesian realm, there is a strong research on Bayesian model averaging. It's called Bayesian model averaging or dynamic model averaging. And yeah, this is, I think, one of the cutting edge researches right now, because you may have thousands of models, and the goal is to combine them and to select which models are really bad, which models are really good. And moreover, there are cases when one model is the best for some period, and after some period the situation changes and another model is the best, and then the first model is the best. Weather forecast, One day, Aladdin says it will rain, and it hits the nail. The other day, it will rain, and wow, there is a beautiful weather. And Clara predicted it. So it's not like just one model is okay and one model and the other models are wrong always. There is some combinations. Another cutting edge research, I do research in distributed estimation. This is my field of interest right now. And this distributed estimation is about historically we had say radar, one primary radar looking at the sky. But this is a very expensive instrument, and now we want to use some cheaper instruments and combine their information together. It's connected with the phenomenon. It's a modern phenomenon of sensor networks. It's connected with Internet of Things, where we try to combine the information provided by several sources together. So there is one small like radar, another small radar, how to combine their, say, more imprecise information in order to get the best information we can. Another cutting edge research in Bayesian theory is modeling with, it's called ABC, Approximate Bayesian Computation. The MCMC things are very closely connected to ABC. It's also part of Monte Carlo methods. Now you know that you need a model, a good model, or a solid model. And sometimes we don't even have a solid model. Sometimes we have very bad models, but the model involves some parameters that we want to estimate. And ABC is a way how to estimate these parameters. This is a very, very huge phenomenon right now. So that's it. Any other question? How does Bayesian modeling deal with small data sets? What is the minimal one? Good question. Yesterday I answered it already. If you have one data, you have one data point. It's good. It's good for you. As long as you use reasonable priors, you get results. If I share my screen and where it is here. I will stop my camera. If you look at this, I think it was here. Yeah, just one ping. I need to start from the beginning, sorry. Just one ping. I started. I want to model the probability that if I send a ping to some server, see this one? Yeah, if I ping a Google server, that the ping arrives within 7 milliseconds. Either arrives or not. And I am interested in the probability that it arrives within 7 milliseconds. I started with a uniform probability from 0 to 1 that is not preferring any particular value. After one ping, I would say that the probability of obtaining pong within 7 milliseconds is 0.67. This mean value, 0.67. And the uncertainty is huge. From 0 to 1 looks like this. Generally, after one ping, I prefer, or I tend towards the statement that the ping arrives within 7 milliseconds. The mean after one ping is 0.67. But I'm absolutely not sure about this. This is very important. Think in the Bayesian realm. You can say the uncertainty. If I ping, if I send, say, 10 pings, if I send 10 pings, then after 10 pings, this is this line, I don't know the color name, azure or who knows. After 7 pings, I expect that the pong will arrive within 7 milliseconds with probability 83%. And my uncertainty is like this. So I would say that it arrives within within 7 milliseconds with 83% of probability, and admit that it may be, the probability actually may be between 0.4 to 1 with high likelihood. So this is the cornerstone. You can quantify the uncertainty in your statement. It's not like saying in the frequency statistics, well, the probability of pong coming within 7 milliseconds is 0.8, period. Here I can say it's 0.8, but the probability also might be between some and some number with a high probability. If I send 100, maybe I will use this plot. If I send 100 pings, it would look like say 90, no, 10 to 90, 100 pings. Yeah, we started from prior 1, so we have 90 successes, 10 failures. The mean is 0.8. Sorry, 0.9. And something small, 0.892. The frequentist would say it was 90 to 10, because there was no, in the frequency viewpoint, there would be no prior. The frequentist would say it's 90%, period. The Bayesian would say it's 89.2%, but we admit that it might be between 0.8 to 0.95, say, with 95% of probability. So I know where could I expect the true value to be. So that's it. The Bayesian statistics is very solid for small sample sizes, as long as your prior is reasonable. Of course, if you use a sharp prior in a very bad region, then it will converge in a long time, not after 10 points. So this is the answer. Small sample statistics. By the way, it's a cutting edge research in statistics, small samples. Not only in Bayesian, but in frequency statistics too. Well, if you have any other questions, feel free to send them to Slido. I will, I will focus on it. Now I would like to continue with the Bayesian modeling. Sometimes I hear Bayesian, but the Lord was Bayes, not Beige. It's like Gaussian. It was Gauss, not Gauss. So we often hear, especially from the US guys, Gaussian. Gaussian process is Gaussian process. So Bayesian modeling, part 2. We will focus on two particular models, linear regression and on the logistic regression. I hope you are familiar with linear regression and logistic regression, because I can't immerse into the theory too much. There is not enough time for it. But I think that people mostly know linear regression, at least by heart. So we assume that we have a bunch of data y indexed by I, which are real. This is the crucial point, real. These are not binary. If they were binary, we can't use a linear regression. Or, well, we can, but the results won't be reasonable. And there's some scalar or vector feature xi. Me being a statistician, I prefer predictor or regressor. In machine learning, there's often the term feature. Oh, let's call it features. For instance, we will use this data set. Here, the data y is the distance of a moving object in meters, measured by a noisy instrument. Why noisy? Because otherwise it would be a deterministic problem. But noisy instrument makes this a statistical problem. The only feature that we have is the time measured in seconds. So we have time, 0, 10, 100 seconds, 200 seconds, and etc. up to 500 seconds, and the distance, 0, 200, 400, and so on. The measurements are noisy. This is important. The measurements are noisy. Even if you have radar, the measurements are noisy. This is why we employ statistical approaches to this. In the field of signal processing, it's called statistical signal processing. And the radar is the statistical signal processing problem. So clearly there is a linear trend, and probably a straight line through the data could explain the data evolution. The straight line model would look like this formula. Yi is expressed by some intercept, beta 0, plus some slope beta 1 times the time, x, and the noise. The noise that corrupts the determinism between time and distance. Mostly we say that the noise is Gaussian, normal, and zero-centered. The zero-centering is a crucial idea here, because if we don't have zero-centered noise, we would have a systematic error, and we would add some constant to each measurement. We want zero-centered noise. Often we want that the noise has a constant variance. In the basic or ordinary linear regression, we assume that sigma is constant. We usually rewrite the regression model into a matrix form, where the observation or measurement or data is given by some regressor times the vector of regression coefficients, beta 0, beta 1, plus the noise variable. A good question would be, how do we know that the noise is normal? Well, we never know that the noise is normal. We often assume that the noise is at least approximately normal. If we had outliers, a popular solution is to employ the Cauchy distribution, but then the calculations may be somewhat complicated. So we would like to fit a line through the data, straight line through these data. And simultaneously, this means to estimate beta, the vector beta, consisting of the slope and the intercept, beta 0 and beta 1, reversed, and the noise variance sigma squared. Once we have betas, we can fit the line there, and once we have sigma squared, we can at least say what the noise properties are and what the future development of the data is expected to be. So we are Bayesians. We have a model for Y. It's the normal model. Normal model in this form, sorry, there should be capital X. Normal model given by a linear regressor being the mean value of the distribution and influenced by some noise with variance sigma squared. And we need to estimate beta and sigma, or sigma squared. Usually we estimate just sigma. For this, as Bayesians, we need some prior. Let's say that for the prior distribution for beta is also normal, with some hyperparameter m and some hyperparameter s. This is the mean vector. Its dimension is 2 because the dimension of beta is 2. And this is the covariance matrix, which is a matrix 2 times 2. Next, we have sigma, which is strictly positive. A convenient distribution for this is the gamma distribution, with hyperparameters a and b being positive real numbers. Good question would be, can we choose other priors? Yes, we could. First, if we want to estimate beta and sigma squared, there is a convenient conjugate prior distribution, which is called the normal inverse gamma distribution. And the nice thing is that if we use the normal inverse gamma prior, we end with normal inverse gamma posterior. And using Wikipedia, we can find what the mean is, what the predictive distribution is in an analytic form. That would be great. However, we may want to estimate beta and sigma separately by using two separate distributions. Why normal? Why normal for beta? What we need is a distribution that is defined on the real line, or in this case, on our real on a two-dimensional space. We could, of course, use any other which has these properties, or at least we could use a distribution, say two-dimensional or uniform, but we need that it covers the true beta. If it does not cover, the estimates will converge as close as possible to true beta, but the convergence will stop on the border of the uniform distribution. Yesterday we have studied this case. For sigma, which is strictly positive, we could use any distribution, virtually any distribution. We can even use the normal distribution, but we would need to use some techniques to prevent computational issues. So gamma is quite a frequent choice for sigma. Next, what we need is to define some, or to set some values for M, S, A, and B. So the data code looks like this. The data block contains N, which is the number of observations. We always used this number of observations in our simulations. The number of regressors. Okay. The design matrix. If you are familiar with linear regression, you know what the design matrix is. It's just a matrix which contains the regression vectors as rows, and the observations here combine in one vector, where each element is one observation. We may want to set the hyperparameters, these M, S, A, and B, externally. Previously, I hard-coded the hyperparameters into the data code. If you look here, this was the estimation of the rate of the exponential distribution. You see that I hard-coded the hyperparameters into the model code, but I may set it externally. Yeah. So hyperparameter M for the normal prior, I will set it external. I will set it externally. The covariance matrix S. Can you see this? Cov matrix. In this case, Stan knows that the matrix S will have some special properties, like being positive definite. Hyperparameter for gamma prior is a positive real. Hyperparameter for gamma prior B is again positive real. So M, S, A, B. M, S, A, and B. The data block. In the data block, I express what I will set externally. Next, the parameters. The parameters to be estimated are beta and sigma. Beta is a vector of length k, in our case 1, no 2, and sigma is positive real number, noise standard deviation. So the model will be composed of normal, normal, gamma. Normal, in this case multinomial, because beta is multivariate. Gamma, normal. I think it's pretty straightforward, isn't it? And now let's compile Stan model, and we put their data code. So we will compile it. It will take some time. So we have some time to proceed before it gets compiled. We need to prepare the data block. The data block, which corresponds, the data dictionary, it's the Python dictionary, which corresponds to this data block. We have to set X, N, K, Y, M, S, A, B. N, K, X, Y, M, S, A, B. Do you see it? Just the data block. The data block describes what will be provided externally. X are my observations, and these ones for the offset or intercept. N is the shape of X in the first dimension, that is the number of observations. I could say, I could write here, y dot size is the same. K is the number of regressors, 1, 2. Y are the observations, and now M as AB. These are my hyperparameters that I decided to set externally. By the way, what's the advantage of setting hyperparameters externally and not here? It's simple. If I set it here and compile it, it takes time. If I set it externally, it's easy to use it directly. So if I want to make a change, here in this case, I change only this dictionary. If I set it here, I need to recompile the whole block, which is time consuming. So still compiling, and it's ready. So bang, error. Y is not defined. Did I run it here? This is compiled. Great. What hyperparameters I used? For beta, for the vector of regression coefficients. Look here. Beta is the mean vector for regression coefficients, and S is the covariance, which express my knowledge or my uncertainty about beta. So I said that beta will be, the prior will be centered at 0 in the origin. And the uncertainty is a diagonal matrix with 10 on the diagonal. Very often we use diagonal matrices for multidimensional normal distributions if they serve as priors, because we don't know the covariances. We just want to set the variances and these lay on the diagonal, on the main diagonal. And AB are the hyperparameters of the gamma distribution. And yesterday I said that if you want non-informative or vague gamma prior, then a convenient choice is A and B to set 0.001. Well, I talked about burning, thinning, running multiple chains 1 hour ago. So here, let's use it. We will fit this model with sampling, a sample from the posterior. We will use this dictionary as an argument which we will use for feeding the C++ code. We will want 20,000 iterations of the Markov chain Monte Carlo algorithm. Warm up, let it be 1000. That's the burn-in period. I don't know why it's called warm-up here when most people talk about the burn-in period. So warm-up here is 1000. I will, or the software will drop the first 1000 samples, because if it started in a wrong place, these samples would be likely to contain samples which are really not from the posterior distribution. Thinning. I want to suppress the correlation. I want to suppress the dependence between the samples. So I will store every other sample. I run two chains so that I can compare whether if the result will be two nearly identical posteriors, I would say that the convergence was just fine. If I will see that there are two posteriors from each chain one, and these posteriors will be significantly different, I would say, wow, there is a problem. Each chain should produce nearly the same result. If it does, I can combine the samples in order to have much larger amount of samples, and verbose is true. So I run it. Beta 1, it's beta 1 and beta 2 stan indexes from 1, like R. Python, C, C++, and other programming languages index from 0. So what's beta 1 here is there's beta 0. What's beta 2 there? It's beta 1. So the intercept is expected to be 1.51. The standard deviation is 1.23. It's quite a lot, I think. So the intercept lays in somewhere between minus 0.9 to 3.92 with 2.5%, 97.5%. If you subtract it, it's 95%. So at 95%, the intercept value, the true intercept value, is between minus 0.9 to 2.34. Sorry, 3.92. The number of effective samples, 15,000. We did 20,000. Dropped first 1,000. From the rest, we saved every other, but we combined two chains together. This is why 15,000. For the slope, the mean is 3.01. The standard deviation is very tiny, so it's very concentrated. The true value of beta 2 is between 3 and 3.02 with probability 95%. Solid. Sigma, the standard deviation of the model of the noise, or the external noise of the noise that makes the data not to lie on a straight line but being scattered around it. This epsilon is Gaussian and has a standard deviation sigma, or variance sigma squared. So the standard deviation has a point estimate 14.81, and the standard deviation of standard deviation, the uncertainty expressed by standard deviation of the posterior distribution is 0.47, and we may say that the true standard deviation of the noise is between this number and this number with probability 95%. So and here is the log probability. I will cut this. We are interested in the posterior distributions, how they do look like. Wow, I see here two distributions. Why? Because first chain, second chain. I have two chains. I have two sets of samples from the posterior. this is pretty solid. They are pretty close. For beta 1, the same. This could be maybe slightly more better, but it's still very solid. For sigma, perfect. Here we have the trace plots of both. The trace plots are quite nice, I think. So we have some point estimates for beta, for the intercept, for the slope. We may do point predictions. For this purpose, I will use the posterior means. Here are the means for the intercept from the first chain, from the second chain, for the slope, first chain, second chain, and for sigma, first chain, second chain. This is the log probability. So what should I do? I have two numbers. I can average them. So I do averaging. So now I have the first posterior mean, the second posterior mean, and the third posterior mean. Slope, intercept, slope, sigma. We need only the intercept and the slope for interpolation. So if I use the slope and intercept and use them for construction of a straight line, the yellow is the straight line, which is estimated using the Markov chain Monte Carlo for this particular linear model with these data. So this is how it works. There are some questions. I will look at them shortly. Strictly speaking, the Bayesians should not be interested just in the point predictions. We call predictions do not mean necessarily that you look into the future. This is why sometimes people use the term forecasts, but we use predictions for the future too. We are interested in posterior predictive distributions rather than point predictions. Yesterday we focused on posterior predictive distributions. If you remember, it was this problem of estimation of the rate of the exponential distribution. Here it would be slightly more complicated. So I skipped this, but it's very easy to learn about it. What you need is to look into the manual regression models, if I remember correctly. It seems that I don't. Here. Prediction, forecasting, and backcasting. You need to provide the new values of regressors for predictions, and then you would need to plot the predictions, including the confidence regions. So I skip this here because it's slightly more complicated. It's again about integration of the parameters out, and then regression. It's somewhat tedious to get the idea. However, for point forecast, it's pretty easy because I only feed the same model with the future regressors. Recall this: the regressor here was time in seconds. So I just put the time 500, 501, 502 up to 600 seconds. Pretty easy, isn't it? So this is the point prediction. In in the frequency statistics, there will be the confidence band, and in the Bayesian statistics, there should be the predictive distribution, or more precisely, the confidence region for these predictions. So that's it. This was the linear regression. I will check the questions. If I have, Olga, if I have some set of, for example, 10 to 15 data points from experiment, typically they are not normally distributed. How can I choose proper prior distribution? Could you advise some method to fit small data set? I will switch the camera on to be a living organism. Here, stop share. Bank. Hope you see me. If I have a set of, for example, 10 to 15 data points from experiment, typically they are not normally distributed. How can I choose proper prior distribution? Well, I'm not sure whether you really want to talk about the proper prior distribution or proper model. The thing is that you need to, first, you need to choose a proper model. If you have data that are typically not Gaussian, a good idea would be to try to decide some convenient distribution, e.g. from the histograms. And this is always tedious task to decide what was the correct model, or, well, correct model. No model, all models are wrong, George Box. But which model is convenient, at least, which is convenient. For 10 to 15 data points, probably you need to use some domain knowledge for this, because you probably know what the data represent and how you expect that they behave, what's probably the distribution of these data. If you don't know, there are mixture models, so you can mix several distributions. Once you know the once you know the model that you're supposed to be sufficiently good, then you have parameters in this model that you want to estimate. And then if if you want to estimate parameters, you need to decide, is the parameter real or is it discrete? Is it negative? Is it positive? Does it live on the whole real line? Once you know these properties, then you can choose a prior distribution. If you want to use, or it would be probably wise to use a flat prior distribution, unless you have some domain knowledge. For instance, if you have data of a rocket velocity, then you have some domain knowledge that the rocket velocity probably is not 10 kilometers per hour. So you can limit or concentrate the prior distribution on values that you suppose the rocket velocity really is, and then let data speak for themselves. That is, let the data update this prior knowledge. Could you advise some methods to fit small data set? This is what I talked previously before the linear regression. If you have some domain knowledge, use it. The rocket velocity is from some number to some number. So limit your prior distribution to this region. If you have some data from the past, you say measured rocket velocity in the past on 20 another rockets, and you know that the rocket velocity is, say, I don't know, 1000 kilometers per hour. You can try to set the prior distribution that is slightly peaked at 1000. So you reuse the domain knowledge, or the past data. But the small data sets, the nice thing about the Bayesian statistics is that you can say some result and you can say how much certain or uncertain you are when it comes to this result. This is the way to approach the problem. I hope I answered the question. Roman, is there a good way to fight systematic error? Systematic errors are a huge problem in modeling. If you have an instrument, say, that has some systematic error, you often know what the value of the systematic error is. If the systematic error itself is a random variable, then you have a big problem. Say if you measure velocity of a rocket, if you measure the velocity of a rocket and your radar says it's 1000 and itself adds 100 kilometers per hour, and at the next measurement it adds something else, and in the next measurement it adds yet something else. The problem is really complicated. It's enigmatic, and I'm not sure that there is anything convenient for this. By the way, this is the reason for the existence of sensor networks, because one sensor lies a bit, another sensor lies a bit, and you hope that if you combine the imprecise information, that the precision will slightly increase. You simply hope that their statements, their false statements are contradict and average out. So that's it. Probably systematic errors. The best way for dealing with systematic errors is to use, if it's if it's possible, to use more data from different sources. Anonymous, could you explain how we should choose prior and how it will influence if we take a bad choice? Yeah, I talked about this yesterday. If you don't have any knowledge, a good idea is to use a vague prior, which means a flat prior, a prior that does not give preference to any particular value. If you choose a bad prior, first, if you choose a prior, and I'm not sure whether I have it, whether I have the simulation from yesterday here yet. Was this one? I think so. Yeah. This was a typical choice of bad prior. I wanted to estimate this was the time to event modeling. I wanted to estimate the rate of the exponential distribution. The rate parameter lambda describes the waiting time, the average waiting, or the reciprocals of the average waiting time. Yesterday I said there prior which is uniform from 0 to 10 instead of the gamma distribution. If you look at the results, I think, yeah, here. In fact, the true lambda was 50. However, the prior distribution was limited from 0 to 10. So it does not cover the value of 50. So it tries to converge as close as possible to 50, but the boundary is 10. It can't go beyond 10. So this is clearly wrong prior for this estimation problem. You can see it then from the predictive distribution, that the predictive distribution, the brown one, does not cover our observations at all. So this is a wrong prior. Another difficulty could happen if we choose. Do I have it here yet? If we choose an incorrect or too narrow prior concentrated on a wrong region. For instance, here, oops. Or maybe I can show it on the regression example, because fortunately here I set the hyperparameters externally, so I don't need to recompile the code. The estimated sigma was 14.81, or the estimated beta 1 is, the point estimate is 1.5, and the other beta 3. So let's set a completely stupid prior. Let's set the prior to be centered at 100 for beta 1 and 100 for beta 2, and say that the variance of these prior estimates is very tiny. So this is a very narrow prior distribution concentrated on the values of 100, while my correct or more smart approach indicates that the true means are 1 and 3, around 1 and 1.5 and 3. So 100, it's really off. Let's fit. Oh, it converged. It's perhaps because of it converged relatively in a relatively sad way. A surprise. What a surprise. 0.01 and 3. I'm really surprised. So I will set here another wrong things. So now I'm interested. Still quite solid. The sigma is off now. It was 14. And the standard deviation is very tiny. And this is wrong. if I plot the posteriors, still quite solid, but it's because of betas. The beta was 3 and 1.5. So I will corrupt it much more. Yeah, now it's still not that bad. There is something with beta. The problem I'm having here actually is a good way, is a good thing, because it shows that the Hamilton and Monte Carlo is able to solve these issues. So it's hard for me to perplex it. If it were some more basic Monte Carlo method, like the Metropolis algorithm, it would fail. So here you can see how robust the stan is. Yeah, still good, incredible. The sigma is now still off. The true value, it's 1, and in fact it was 14, but the estimates of the regression coefficients are still very solid. What you can observe here is the standard deviation. This also indicates that something is strange. If the standard deviation, or if the parameters are so concentrated, if the posterior is so concentrated, look at it, 0.01 to 0.05. This indicates that perhaps something is strange. Of course, you need to check the magnitude of the data. 3.0128, 3.0136. Yeah, this is often if you have data which are in hundreds, and such a simple model, then this strong concentration is says that something is probably not well set. But if you look at the interpolation is still solid. This is incredible. Even I didn't have the idea that stan is so robust. Anyway, if you choose bad or wrong prior, inconvenient prior in the Metropolis algorithm, or if you choose a bad prior in as a conjugate prior, where the result is analytical, then you will end with bad results. You multiply. I multiply 100 times. Yeah. My fault. My stupid fault. I noticed that here is zeros. Sorry. Thank to Anonymous. Thanks. Thank you so much. I thought that I forgot to change zeros to ones. So stupid mistake. So the fitting takes time. I was also surprised. So come on. This prior is extremely, really extremely bad. There is some adaptation in Stan, and it seems that it tried to adapt somehow. Yeah. Muchas gracias, Anonymous. Mean for, or point estimate for the intercept 10,000, for slope 9,996, for sigma this huge number. So you can see that if you set a bet prior, the results are bad too. Even the standard deviation here is very tiny. So again, this indicates some problem. The problem with the prior. Do you see it? Here, we have still something like a solid posterior, but this is absolutely wrong posterior. It's not something which makes sense. Here, if you look at the trace plot, again, this is not a trace plot of a convenient or acceptable Markov chain. I think that the plots, do you see the plots? These are the real data, and this is the distance in a magnitude of 1/6. So this is the way how to set an inconvenient prior, and you will realize it from the results. Now I will send something less stupid than those terrible orders, and we will see. It was much faster. You can see there was not so much trying to adapt. Still some strange numbers. Here the plots look relatively reasonably. For beta 1, which was 3.5, it's not totally off. For this it is, and sigma is wrong too, but the posteriors look quite reasonable. So if we check the plots, we can see it does not interpolate your data. So you always need to do proper checks. So, Kamil, another question. One of the advantages of Bayesian modeling is possibly to estimate some confidence interval for true value of the parameter. But for instance, there exist formulas designed to estimate confidence interval of regression coefficient without extra modeling. So why do we need this more complicated approach? You probably mean the the confidence intervals from the ordinary statistics. That's true, but the interpretation is slightly different. In Bayesian statistics, if you have 95% confidence interval, it means that the true but unknown and estimated value of the parameter lays in this confidence interval with probability of 95%, period. In frequency statistics, it loosely speaking means that 95% of computed confidence intervals will cover the true value of the parameter. period. So the interpretation is slightly different. It's not about making a 5% of error in the sense that there is a 5% chance that your frequentist confidence interval does not cover the true parameter. So that's it. The Bayesian interpretation is pretty straightforward. Or we may focus on Bayesian hypothesis testing. The Bayesian hypothesis testing tells you whether zero model, zero hypothesis is true or not, and with which probability. In the frequentist hypothesis testing, you either say that you reject the zero hypothesis or you fail to reject it, and you do this at the confidence or at alpha, say 0.05, but it doesn't mean that with a probability of 5% you make a mistake. There are two types of errors, and this is not so straightforward. So the interpretation in the Bayesian statistics is much more straightforward. This is a problem we statisticians often have with the interpretation of results in say non-statistical fields in biology or in economics, because the people there often misinterpret their results. And what is even worse, sometimes in the field, say alpha, the critical, I forgot how it calls in English. Well, the alpha is 0.05, and the people don't know what exactly this is. In the Bayesian, from the Bayesian viewpoint, we can say that we have 5% of error. So that's it. I suggest there is an article on Wikipedia which compares the confidence intervals, the confidence intervals in the frequency paradigm and in the Bayesian paradigm. Significance levels is alpha. More complicated approach. I don't know whether the Bayesian statistics is complicated. I think when I started with Bayesian statistics, I was familiar with the frequency statistics, and for me it was hard to grasp it. But it was only because it's about philosophy. It's just about philosophy. The only difference thing is that you use prior information and you use distributions for representing your knowledge. This does not exist in the frequency statistics and in related fields. So it's only about adding the prior. On the other hand, what I found quite quickly is that the interpretability of the results is much more straightforward. In frequency statistics, you often need, you often see that people reject the null hypothesis, or that they accept the null hypothesis, but we never accept the null hypothesis. We either reject it or fail to reject it. And the classical question of our students is, if we fail to reject it, does it mean that we accept it? No. The critical point is to explain that if we don't reject it, it means that we don't have enough evidence to reject it, but we never have enough evidence to accept. I hope this was sufficient. How do we calculate the likelihood in this case? We are sampling beta, sigma, and calculating the probability of obtaining our real point y from the normal distribution. How do we calculate the likelihood in this case? We are sampling beta, sigma, and calculating the probability of obtaining our real point y. Sorry, I don't understand the question in this case. How do we calculate the likelihood and if we are sampling beta, sigma, and calculating the probability of obtaining a real point? May you rewrite the question whether it connects to our particular example or because when you talk about likelihood, it sounds like the maximum likelihood approach, and I don't know whether it's connected to it or. So please try to edit the question. I will get back to it. Roman, have you ever encountered use of Bayesian approach in classical clinical trials? If yes, could you please describe your experience in detail? Clinical trials are often about Bayesian statistics because if you calculate all those sensitivities and specificities of say medicaments or drugs, it's about the Bayesian statistics. Quite surprisingly, in these trials, the Bayesian statistics was used even in years where the Bayesian statistics was say politely overlooked. So if you want to know more about this, try to check the literature dealing with testing of medicaments. When we are now having the COVID era, I did some modeling for my students. It was about testing the. There was an idea that the government should test nearly the whole nation using those rapid tests. And I calculated for my students what would be the result, because the rapid test has some specificity and some sensitivity, which means that whether it detects that you have COVID if you don't, and vice versa, whether it has, simply speaking, false positives and false negatives. There is some there's some prevalence saying that the population in my country we have 10 million of people. It was expected that approximately 20,000 people were already in contact with COVID somehow, and most of them were never detected or never diagnosed. So I calculated, and the result was that if we did testing of the whole population using rapid tests, very solid rapid tests, we with I think 400,000 positives, most of them being false positives. So it would be from the economical viewpoint, it would be a total nonsense. So this is where you can use the Bayesian approach too, because the prevalence is the prior. So how do we calculate the likelihood in this case? We are sampling beta, sigma, and calculating the probability of obtaining our real point y from normal distribution. I see. In this case, you need to use the posterior predictive, because you have beta, you have an estimate of beta, but you have some uncertainty in this estimate. And you have some estimate of sigma, and there's also some uncertainty. If you plugged the point estimate of beta and the point estimate of sigma into the model, beta times x with variance sigma squared and being normal, you would neglect the uncertainties about your estimates. This is the critical point. If you neglect these uncertainties, by the way, do you use the as the point estimate mode or the mean value or what? Or the median? You can use all. So which one do you choose? This is the point. So you aim at obtaining the posterior predictive distribution and then look where the y is located with respect to this posterior predictive distribution. The posterior predictive, if you used the normal inverse gamma conjugate prior for estimation, the posterior predictive would be student distribution, fortunately centered at the same point as the normal model, but with a wider with a higher variance, with a higher uncertainty, because the uncertainty of the posterior predictive is the combined uncertainty of the model, which means the noise variance, the uncertainty about sigma, and the uncertainty about beta. So we use the posterior predictive to measure how the model fits the actual value of y. By the likelihood, I meant px and theta posterior. Yeah, I got it. So instead of using directly the likelihood, we use the posterior predictive, which is somehow more complicated, I admit. So I hope I answered the question. If not, ask again. MCMC for multidimensional distributions. Yes, absolutely. And what we did in the linear regression, our sigma was one dimensional, but our beta was beta 0, beta 1, or with the Stan indexing beta 1, beta 2. It was two-dimensional. So definitely yes, MCMC for multidimensional distributions. There was a big problem with MCMC with the Metropolis algorithm in multiple dimensions. This is why the Gibbs sampler was developed, because it was able to just proceed on marginal distributions. Yes, for multidimensional distributions, perfect. Andrei, from yesterday, I'm more or less confident what we talk about the Bayesian regression estimator as an asymptotic unbiased. Does it have any precision benefits to maximum likelihood regression estimator when it comes to estimation of posterior moments in finite samples? Again, I'm not really sure that I understand the question. Generally, the maximum likelihood estimator converges to the true, if there were any true, regression coefficients. The Bayesian estimator converges also to the true regression coefficient. The benefits are that we may quantify the uncertainty about our estimates first. that we may do predictions that reflect this uncertainty. That is the prediction confidence regions, and we may say which model is better because we have solid measures of the model quality. So we may combine models. Combine models, it's good. We may perform hypothesis testing with these models. What next? If we used the approximate Bayesian computation approaches, we may even use models where we have complicated or intractable, I would say, likelihood, which means the probability distribution for the data, for the observed data. So we have much more tools in our bag for dealing with data. Even that combination of models. If we focus on say, let's model some phenomenon, be it what? Let's say I have a bunch of radars, simple, easy radars with very noisy, very imprecise measurements. One of the radars employs some wavelengths, another radar employs another wavelengths. I can model the trajectory of my flying object using data from each of these radars, and I can combine it together. And I may assess, well, this radar is really wrong, I don't want to use it. Game theory. Full-time C++ developer. It's interesting promotions. So this is the reason why we are interested in Bayesian modeling, Bayesian regression. Finite samples. That's the frequency statistics assumes repeatability of the experiment. And states that the model will produce observations in the same way as now. It's the repeatability, frequency. The Bayesians admit that the data are the only thing that we have, and that the model maybe will not produce the same things in the future. So we have uncertainty. So Andre, I hope I answered your question. Anonymous, a bit confused with sigma here. Usually it's represented as a covariance matrix, but here's just a number. Also seems strange that given that there is a clear correlation of the chart, the slope is much lower than sigma. Slope isn't statistically significant. Statistical significance, this is important in the classical frequency statistics. I wouldn't talk much about statistical significance in Bayesian statistics. Sigma. What sigma here? Sigma in this case comes from this formula. Each observation is described by a regressor, xi, in our case time, multiplied by some factor, plus some additive factor, plus some noise. That's the important thing. Plus some scalar noise. Why scalar? So epsilon is scalar too. Epsilon, in turn, is a random variable, which is scalar. It's a zero center because I don't want to have any systematic error there. And it has its variance. you may imagine that for each particular measurement of the distance, we have, the distance is scalar, we have some error of say, measurement. And this needs to be scalar too. The covariance matrix, if the measurements were two-dimensional, say longitude and latitude on Earth on a map, then of course epsilon would be two-dimensional because you would have an error in longitude and latitude. And instead of scalar sigma, we would have covariance matrix, capital sigma. So that's it. I hope this is clear now. Seems strange that given there is a clear correlation on the chart, the slope is much lower than sigma. Slope is much lower than sigma. No, the epsilon, the noise, is additive here. It's a random sampling from normal distribution. It's not correlated with neither the intercept nor the slope. It's a random number which is added to each point. Unless we had epsilon here, I don't have raw data. Unless we had epsilon here, it would be straight line. And what makes the shift in the vertical axis is this epsilon, this additive epsilon. I hope I succeeded in explanation. If not, drop me a message. So I know that it's necessary for ordinary OLS to standardize normalized input data. Is it the same with Bayesian linear regression? Well, for ordinary least squares, you need to have similar magnitudes. This is why we often do standardization of data or normalization of data or any convenient transformation of data. In the Bayesian linear regression, it's quite usual to transform the data. Yes, it is. If you have, for instance, if you have two-dimensional measurements, and you have time in microseconds and distance in astronomical units, that's really, or the astronomical units is not a good example. In thousands of kilometers, and it's a really good idea to normalize the data to have similar magnitudes. Yep. I think that the data transformations are generally a valid procedure, and it's not particularly connected with some concrete methods. I think it's a general way how to deal with data, how to preprocess the data for any subsequent analysis. Hope I answered. Again, if you have any questions, drop them. Well, I will continue with logistic regression. This is the last example in our course. And yeah, let's go. In the linear regression, we assumed that the data is real. In the logistic regression, we have binary data, zeros or ones. Zeros with some probability, ones with some other probability. These probabilities sum to 1. What's the problem here is that we want to connect the linear regressor or linear predictor with the value of observation, with this 0 or 1. So there needs to be some transformation. We call this class of models generalized linear model because the linear part is in x times beta. As in the linear regression, x times beta, the linear predictor. In the logistic regression, we have x times beta. That's the linear part. And the generalization is in using some function that transforms the result to a convenient region. Here we have binary data, 0 or 1. So in this case, the logistic regression employs the logistic function as the inverse logit function that transforms the linear predictor x times beta to the interval 0 to 1. So the expected value of my observation is the probability of we will see that binary distribution, which is logistic or logit to the minus 1, logit inverse of the linear predictor. This is the logit function, and this is the inverse, the logistic function or sigmoid function, sometimes called. You can see that it converts the real line to the interval from 0 to 1. By the way, this is somewhat strange because we have a binary variable 0 or 1, and we model it as a continuous variable from 0 to 1. But we don't have any better transformation. So we know that 0, 1, this is the binary distribution, and it has a parameter p, probability. In this case, pi, a probability for each observation. The mean value of the binary distribution is this p. And I know that this p is the logit inverse of logit function of the linear predictor. Wow, how trivial. I hope you are somewhat familiar with the linear regression because sometimes thinking about this makes headaches. So we have Bernoulli logit. So Bernoulli logit in Stan. I have a real world example here. It's a classification skin and non-skin. I really love this data set because it's so good for determining how well the classifier works. The skin non-skin data set was published by two gentlemen, Butt and Dahl. It has some nearly 250,000 samples, of which nearly 51 samples are skin samples and nearly 2,100 samples are non-skin samples. This dataset actually was collected by selecting a random pixel from a picture of faces. And these faces were for various age groups, young, middle, and old, and race groups, white, black, and Asian, and gender. There were two databases that were combined for this purpose. Each data item consists of 4 values, B, G, and R, blue, green, and red, and the class label. We have how it looks originally, B, G, and R, blue, green, red, and class. 2 standard for face and 1 for skin and non-skin. I'm not sure now. But we may look at it as 2 classes. What we needed to do, and I already pre-processed the data, was to subtract from the last column to make it 0 or 1s. For modeling, we may want to use the linear regression in the form BGR for each sample, and the 1s representing the offset. In the linear regression with a straight line, it was the intercept. So here we call it usually offset. If we allow the data from CSV file, we have B, G, R, and class 0 or 1. I think that skin samples are 0s and non-skin are 1s. So the linear regressor should look like 1 and BGR values. Quite nicely, we can model the intercept or the offset separately. So we don't have to add those 1s to the vector BGR. Stan will do it for us. So the design matrix looks like this: B, G, and R. Another B, G, and R. Each row is one record. Next, we create a vector of observations, which means that we select the last column. And let's look at the Stan model for linear regression. We have n observations, which are integers. Sorry, the number of observations is integer number. The number of regressors excluding the offset, because the offset will be Stan will work with offset for us. The number of observations, the observations themselves, I, which are integers, 0 or 1, and the regressors, which are raw vectors, excluding the offset. The parameters are beta offset, and the rest of betas for B, G, and R. I think this is pretty straightforward. The model is Bernoulli logit, and here is the linear predictor. X times beta plus offset. I think straightforward, isn't it? For each of the data. And the beta offset, let's have a normal prior for it, centered at 0, and with standard deviation of 10, which means a quite nicely flat prior. And the rest I haven't specified. If I don't specify the prior, Stan will use uniform prior. In fact, it will use improper uniform prior. But it should end with a classical posterior distribution. So let's compile. It will take some time, so we will look at the rest. I need for this data block to set the n, k, y, and x. N, k, y, and x. Here I said that y is integer, number of samples, number of observations, dimension of regressor, p, g, and r, so 3, and regressors combined in a matrix. So it's still compiling. Come on, compile. Compiling. I would like, well, let's look at what we will do next. I will print the data and perform fitting. I will do 5,000 iterations of the MCMC algorithm, which is not very much. The warm up will be 1,000 samples, or the burn in, in order to suppress the potentially invalid initial information. Done. The thinning will be 2, so every other sample will be stored. I will run 3 chains. Why not? Just 3. And the variables true. So if I look at data, I will have y there, which are my observations. N is 5,000 samples. K is 3. I use 3 regressors. X are those rows on this matrix. So still fitting. Fitting. Let's print the fit when it ends. Here it's nicely obvious how teaching Markov chain Monte Carlo is time consuming, because we still need to wait for sampling or for compilation. If we had some more complicated models, we could start with it as a whole session and then wait for the result for, say, 80 minutes. That would be a strange course. So come on, calculate. There is, by the way, there is an adaptation of the Hamiltonian Monte Carlo in Stan. This allows to adapt the algorithm or the setting so that the result is obtained, or the quality of the result is improved. This is why sometimes we have to wait for the results. You see that I just have 5,000 iterations. Yes, I have 3 chains, but these 3 chains may run in parallel, but only 5,000 iterations, and it takes time. So come on. There is a question that I might. I will answer it in a second. So the result, the offset is 4.27. Its expected value. Its point estimate. The standard deviation is relatively small, and the true value of the offset is expected to be between 3.91 to 4.65 with 95% of probability. Similarly, the point estimate for the B, blue, green, and red. So, if looking at this, what does it mean? Green, BGR, blue, red. Maybe people are violet, but definitely people are not green. There is no complaints from Stan, so we can plot the inference data. Here we see that there are three different or slightly different, nearly identical posteriors for each chain, one posterior. Beta offset, beta 0, beta 1, and beta 2. They are very similar. I would be satisfied with this. The trace plots look relatively well. We may try to compare our estimates with those of maximum likelihood estimator in scalar, by the way. These are estimates of Stan for each chain, and this is a maximum likelihood estimate from a scalar. Very similar. Very similar. The scalar provided the estimates much faster, but I don't have any idea of the uncertainty. From which to which value could I expect beta offset, beta 0, beta 1, and beta 2 to be? I don't have any convenient way how to say that this model is better than another model if I used just MLE. Yes, I could calculate the confusion matrix and decide what the precision and the recall and etc. is. But I can use methods from the Bayesian statistics to combine multiple models. But how could I combine multiple models in that use MLE? Of course I can, but these would be very heuristic approaches. In the Bayesian realm, these approaches would have relatively solid theoretical interpretation. So we can see that the results from the Bayesian estimator are similar, very similar to the result to those of the scalar. Natalia had a question. Why do we need a for loop in logistic regression in the model block? We didn't have it in for linear regression. The question is this. I have a for cycle here. Can I open? Oops. Yes. To be. Oh, it was not what I wanted originally, but doesn't matter. Side by side. So this is the above is the code for logistic regression, and here is the code for linear regression. Here I have a for cycle for each particular measurement and for each particular regressor. Here I don't. The answer is simple. For some problems, the stan can work with matrices and with vectors. This is the case of the linear regression. This one. I fed it with X, which is the whole design matrix. Beta, it's a vector, and sigma is just, yeah, maybe the question about the sigma, why not matrix? This is a vector y, this case, of all observations. This is a matrix, design matrix, where the rows are individual regressors. This is a vector. So this sigma should be something like a diagonal matrix of the same size as the length of y, and with sigmas on the square. Stan is able to do it internally. In this case, we don't have, at least I'm not aware that there is, I think there is not, anything like this, any possibility to calculate with all observations and all regressors at once. So we need to proceed observation and regressor one by one. And if we focus on the first lecture, I'll close this. If we focus on the first lecture, where I presented the Bayes theorem, where is it? No. Here it is. If I work with multiple observations, I may use a prior and a product of individual models. Did you see it? The first cycle is like a product of individual models. So this is the interpretation. Either everything in one shot, if Stan is able to do this, or one by one. If I remember correctly, and I'm sure I remember it correctly, yesterday we did the same. Here, it was one by one for the Bernoulli. And then house flying lengths. Yeah, house flying lengths was all in one shot, because we fed it with y. And the third example was, again, one by one. So if you can write it, sorry, this is for the predictive. Yeah, just in one shot. So both ways are sometimes possible, sometimes just one way is possible. For this, it's a good idea to consult the manual, the Stan user guide, this guide. So this was the question. Any other question? I hope that I answered this for Natalia. Well, Kamil's back. So I don't see any additional questions. The first part of this day was slightly shorter, and the second part was slightly longer. So in average, statistic is about averaging. In average, it was it was okay. We have one more question from Roman. Is it just me or beta coefficients look like something gone wrong? Betas of RGB themselves look statistically insignificant compared to offset. Seems like looking at the moment, we can conclude that color is not significant in determining if something is skin. One important thing, Roman. If I switch back to this, it's here. The estimated beta is the offset here, 4.27. Beta 1 is 0.03, but you multiply this 0.03 by values like 218, 110, 255. So the result is a reasonable number. Don't look at the absolute values of the estimates. Even values like, well, in this case, the minus 5.6 e minus 3, it indicates, oh, it's raining. It indicates that probably the BG green, the green color does not bring much information. But this is 0.03 times 0.03 times 218 is 6.54 plus 4.27. It's, I think, reasonable. In fact, what we do is this, well, 4.27, 0.03 times this times 211, and the last times 202 for just this row. The result is that we sum values 4.27, 6.54 minus even this. I expected this to be less significant, but it's not that small. Minus 1 point something and minus 6. Great, Roman. Perfect. Well, no more questions, it seems. In case you need to answer something in the future, don't hesitate and drop me a message. It's like from those videos on YouTube. Click like. So drop me a message to either Slack or to my email. You have my email. It's in the first notebook. So if you have any question in the future, today, tomorrow, in next 10 years, drop me a message and I will answer. I'm usually quite quick in replying, so don't hesitate. I wish you the best in your practical dealing with data, and if you start using some techniques from the Bayesian methods, it would be great, and I hope that you succeed, and I keep fingers crossed.
Thank you for this great course. We like it very much. Thank you.
Thank you.